Hello, and welcome to Pitch to Play, the technology behind going from ideas to streaming. My name is Ryan Schroeder, and I'm a senior software engineer at Netflix. Everybody loves a good story, and at Netflix, we love telling stories. Stories entertain us, they excite us, sometimes they make us laugh, and sometimes they make us cry. But stories have a way of connecting people and bringing them together. If you ask me, the best stories end in a happily ever after. Today, I'm going to tell you a story. It's the story that how a piece of content goes from pitch to play. It's not the story of my own, but the story of the many talented individuals with which I get to work with at Netflix. We'll cover some of the technology that we use to get there. But spoiler alert, we're not going to start at the beginning, the pitch. We'll actually start at the end, the playback, and work our way backwards. Why? Because knowing where you want to end up is the first step to getting there. It also happens that the end of our story today, at playback, is the beginning of the story for our members. Anytime a Netflix member wants to choose a piece of content to entertain them, they make a choice. Do they choose Netflix or do they choose something else? It could be reading a book or video games or exercise. We refer to this choice as that moment of truth. These moments, they happen all the time. When our members choose Netflix, we win those moments. But then it's up to us to make sure that we take advantage of that and don't spoil it. Our mission is to entertain people through the very best quality of experience, no matter where they are or what device they're using. Sounds like a simple mission, right? Well, in a way it is, but although it sounds simple, it certainly isn't easy. So now that we know what we're aiming for, we can begin our story today of how a title becomes playable on the Netflix service. At a high level, a title will go through a few key phases. Production, which is where the content is born and it's shaped by the storytellers. Promotion, which is where we get that content and connect it with the audience. Finally, there's playback, which is where that content is enjoyed by millions of people around the world. Each of these phases is vitally important to winning those moments of truth. A title that fails to play is as good as one that was never even created. Perhaps worse yet, a title that has a poor playback experience is distracting from the story that we're trying to tell. Likewise, great content without a good playback experience, is one of those things that our members they don't enjoy. They'll go somewhere else. They'll choose something else. But if we have great content and a great playback experience, but we can't connect that content with our members, then that title or that content never reaches its full potential. And finally, there's the content itself. There are so many wonderful storytellers around the world with stories to tell. We don't want logistics or any operational challenges to get in the way. By providing a service that can produce great content, promote it to our members, and deliver an amazing playback experience on any device, on any time, we'll continue to connect the world through storytelling and win those moments of truth. So if playback is that moment when the three phases come together to entertain our members, what really happens when you click play? But more importantly for our story today, what did it take to get here? When a member clicks play, the device contacts Netflix and identifies itself and its capabilities. What device is it? What resolutions does it support? What about HDR, 4K, 5.1 audio? What are those network conditions like? This information is sent along with the request to Netflix, which is powered by AWS, which in turn respond with a manifest. That manifest contains everything that the device needs to know about how to play the content and which content it is. But the most important piece of information in that manifest is the URL to the encoded media files. The player parses the manifest, fetches that URL, and playback begins. Simple, right? Mission accomplished? Well, In fact, most modern browsers have playback support built right in, just by navigating to a URL of the video. For a slightly more advanced experience, you can load the video with HTML5 and JavaScript. You collect enough of these links, and you have a streaming service. So why isn't it just this easy? Well, we've got to remember our mission. It's all about the quality of experience and the scale that we operate. There are thousands of people that are choosing to watch Netflix every second. Talk about those moments of truth. In fact, so many people are choosing Netflix that video streaming alone by Netflix accounts for almost 12% of global internet traffic at any given point in time. And almost 100% of that traffic is served from our OpenConnect system that we've built, which is a purpose-built CDN for delivering that content around the globe. There are many great CDN providers, so why would we take on that complexity of building out our own infrastructure? In fact, the story of our content delivery at Netflix began by partnering with those CDN providers. But what we discovered was that our single use case of video distribution had challenges that were harder to meet than with a general purpose CDN. Our mission of delivering the great member experience that we're after was sometimes impacted by factors that were outside of our control. Specifically, as it relates to content placement and content proximity to our members. As we continued to grow and scale, we needed to have control over these factors so that we could balance that growth and scale with efficiency. One of the most unique aspects of OpenConnect is that, unlike a general purpose CDN, the content is not filled on demand. Every file that needs to be served from OpenConnect needs to be placed somewhere within the network and distributed appropriately. While this adds a lot of complexity, it allows for that unparalleled efficiency, giving us that control so that we can continue to grow and scale. So how do files get deployed to OpenConnect? We've designed the system to serve content that you want to watch from the OpenConnect server closest to you. This means there are tens of thousands of OpenConnect servers around the globe, each with a portion of the Netflix catalog. There are millions of files to deploy that require petabytes of storage. No one server is large enough to store the entire catalog, so we group servers into clusters. These catalog clusters are located within internet exchanges around the globe. In order to provide an even better experience, we also partner with internet service providers to embed OpenConnect clusters in their networks. Again, this brings that content closer to our members. The OpenConnect cluster that we need to store the entire catalog is often too large. It doesn't fit in the ISP networks. So since some is better than none, we place smaller clusters in ISP networks. But then this provides that critical choice. What content do we put in those ISP networks? We accomplish this by determining the relative popularity of each file that we have to place and using actual historical playback data as well as forecasted demand to know how many files we need and where. Another factor to consider as it relates to popularity is that sheer demand of any given file. The goal is to predict which video files will most likely be accessed by our members and pre-position them so they are as close as possible from a network perspective. That moment of truth that we're after, when a user clicks play, well, that's also the moment of truth for OpenConnect. If we didn't do our jobs right, and if the file's not there, playback wouldn't work. Or if the content is not even placed appropriately, say it's farther away, there's more network hops between our users and the content, playback may still work, but it won't be that great experience that we're after, and you may have buffering or a subpar viewing experience. So it's more than just the distance traveled, however, that makes this a complex challenge. There are throughput considerations. Hard drives, both spinning and solid state, have limitations on how much throughput they can deliver on a single disk. It's possible that some of our content, through some of our files, requires more throughput than a single disk can provide. So we have to put multiple copies of the same piece of content in these various locations. Because content is pre-positioned, We can be opportunistic not just about what is placed, but also when that content is placed. At our scale, it's more advantageous to deploy content when demand is lower. Hard drives have different performance characteristics when they are reading data versus writing data. Doing both at the same time, especially with commodity hardware that we use for OpenConnect, it makes that all the more challenging. By waiting until the demand is lower, we can avoid some of that contention and get better overall performance. But if we have to wait until demand is lower, that means we have to get our predictions right. If we don't do that prediction correctly, we may not have the content where we need it when we need it. We could be operating in that suboptimal state for up to 24 hours. Since we're global, we follow the sun, or in our case, the absence of sun, since we deploy overnight typically, which means that it could take up to 24 hours to get new content deployed. It also means that newly created video files also need that 24-hour lead time before they can be ready for member traffic. To avoid filling the same file multiple times, we use a tier fill model with an OpenConnect, which means the first tier fetches the files from S3, and then from there it gets distributed to the peer network. So imagine the deployment pipeline as a highway during rush hour. Everybody wants to get from here to there. And for our story, the destination is that moment of truth when playback happens. If we don't leave early enough, we'll be late for our appointment, and our members won't get to watch the titles that they want to watch on Netflix. So to avoid those unexpected surprises, just like a busy highway, we've incorporated a fast lane for prioritized deployment. We can't control everything. Files are still late sometimes, and they have to be deployed. So the fast lane deployment pipeline that we have functions very much like our normal deployment pipeline. There's just less stuff in it. If we put too much in the fast lane, it bogs down just like the normal traffic would. So one thing about that fast lane, though, is we have to be careful, since, again, that contention of disk, whether you're reading versus writing, we need to get that content on the disk or playback doesn't work, but we also need those clusters to serve while we're doing that. So it's a delicate balance to strike. Another thing we do is that we deliver multiple URLs to those clients, not just a single URL. This provides different routes to OpenConnect, such that if one route is temporarily interrupted, we can easily switch to different routes by monitoring those real-time metrics. This is all behind the scenes. Our customers don't know any different because the devices buffer that content ahead of time. All of these factors together make OpenConnect a very efficient and reliable delivery network that's part of our story. So if OpenConnect is the system that's delivering the video bits, where do those video bits come from? Well, that's handled by our encoding pipeline. The encoding pipeline is responsible for ingesting the source material, which also includes the video, but audio and time text as well, and transcoding that into something that can be played on the devices. We always want to start with the highest quality source possible, which in practical terms could mean a video file with a bit rate in excess of 100 megabits per second, right off of the camera. Very few, if any, consumer devices could support playback, nor would we want them to. You'd blow through your data caps. In order to be usable by a device, it must be transcoded down to specific formats so that the device can use it. Nothing comes for free, however. That choice of bitrate has a dramatic effect on the quality of the output file. As the source file is being delivered to Netflix, we write it directly into S3. Once the upload completes, we kick off an inspection process that begins automatically determining if the file passes those basic media checks. If those pass, we do deeper level frame-by-frame inspections in order to determine things like silent audio, stuck frames, dead pixels. All of this automated and happens with every delivery. We also perform other processing on the file using a pluggable framework that we've developed. So some of those examples are scene detection and face detection. And we also create a lot of indexes so that we can encode efficiently. So video transcoding is a notoriously CPU-intensive task. Not only that, but it requires a lot of other system resources as well, like memory and disk, just to move and manipulate those files. So rather than perform the encode on a single instance, processing the source from start to finish, we employ a parallel encoding process. In practice, that means that instead of encoding the full hour of content in one shot, we split the content into chunks and encode each portion of it on the order of 3 minutes. Each encoded chunk is written temporarily into S3. Once all of the chunks complete, we fetch them all, stitch them back together, and write it back into S3. So from there, a file is automatically scheduled for deployment on OpenConnect just by writing it back into S3 and making it available. Switching from the serial encoding pipeline to a parallel encoding pipeline also allows us to encode files faster and leverage a wider variety of instance types. It also makes that system more robust, since a failed chunk is easier to recover from than failing the entire duration. We don't have to start all over again. Some of the newer features of the encoding pipeline work to optimize the output files by picking the best bit rate for the best title as a whole and at the individual chunk level. Previously, each title would go through the same parallel encoding process and output the files with the exact same characteristics. For example, every encode that we produce for low bandwidth situations would be 235 kilobits per second. Why 235 kilobits per second? I have no idea, but that was the number that we picked. For medium bandwidth situations, we would get more, and then all the way up to, say, 10 megabits for our high definition in-home viewing. We call this the bit rate ladder. Each title was processed using that same ladder. The more bits that we allocated, the less compression there is, which means there's a higher quality image. But the less bits that we allocate would lead to lower quality images. So after lots of experimentation, trying to find the best ladder to use, we had to accept that what's best for one title may not be best for another title. Cartoons and animation can be encoded at a much lower bit rate before there's a noticeable quality impact. Live action films often require more bits than we were even using on our previous bit rate ladder. The same concept even extends to that chunk level. To achieve comparable quality, action scenes have more motion, which means more bits to achieve quality, versus those static scenes of close-up shots. Because we use parallel encoding, we can now encode and pick the best bit rate for each chunk that we've split off. Because the chunk sizes were a few minutes in length, sometimes the action scene would bleed into the drama shot or to the close-up. And so we weren't able to accurately pick which bit rate for which chunk. Do you allocate more for the action or less for the close-up shots? So to make that bit rate selection even more accurate, now we leverage that scene detection that we do during inspection and literally encode each scene separately, then stitch it all back together. In developing these optimizations, we've had to come up with a new way to measure visual quality. This new measure is called the Video Multi-Measure Assessment Fusion, or VMAF. It's an open source library that we publish. You can use it on your own videos. It works by running complex analytics on the output frames and compares them with the video source. We reduce those results down to a single number, which represents a relative visual quality score, with 100 being identical to the source. By plotting the bit rates of our new bit rate ladders versus VMAF quality, we can visualize those improvements that we're making as we try out new recipes. And then we can compare titles against each other. These optimizations have allowed us to maintain overall visual quality while also picking the optimal amount of bits per title. Each title gets exactly the bits that it needs for what it's trying to show. Comparing these two titles, we achieve 1,000 kilobits per second savings at the highest end, which leads over 5 gigabytes of data transfer savings to our members. I'm currently data capped, and those data caps, they add up fast. Those savings not only impact our members, but also OpenConnect. We can be more efficient if we have to store less or serve less traffic. So as we've seen, we don't just produce one video output, we create multiple for different bit rates. But more than just bit rates, there's different resolutions, different codecs, different formats, Each makes the file unique from one another. For a typical Netflix original, being 4K and HDR, we create over 100 different file variations from a single source video. Needless to say, it takes a lot of computing power to transcode all that video. In fact, for a single source, if you had to cram it all together, it's over 15,000 CPU hours just for one title, which is almost 2 years running nonstop on a single instance. So if we can't do it on a single instance, where does that all come from? Well, for us, we leverage our own internal spot market. So at Netflix, when we plan our regional capacity, we look at how much demand we need to serve customer traffic per region, and then we purchase reserved instances. We also have to account for the failover scenario. We're able to actively move traffic from one region to another, so we have to support that additional load. But we're not always operating in a failover mode, and likewise, the demand is only highest for a couple hours of the day. So what happens is, as the demand lowers, we use auto-scaling to reduce the number of reserved instances that we're using, freeing them up for other use cases. When the demand gets higher again, we scale back up. The biggest consumer of these unused reserved instances is our encoding pipeline. It's constantly monitoring how much capacity is available, and it's adjusting its usage accordingly. Again, we're allowed to do this because we can pre-position that content and plan ahead of time just to make sure we get to our destination. This borrowing from the internal spot market is over 95% efficient, which at our scale leads to millions of CPU hours a day that we can reclaim. So at this point, we've highlighted some of those technology that we use for playback. However, we wouldn't win very many moments of truth if our service looked like this. What are some of the things we'd want to add to make it a more enticing experience for our members? Title, synopsis, release year, ratings, cast and crew, genre, rows. Okay, now we're starting to get there. That's a little bit more like what our Netflix service wants to look like. So each piece of that metadata is owned and managed by its own microservice. These microservices run on compute and are backed by relational databases. They're also fronted by one or more user interfaces. It's those UIs that our internal teams use to make the title available for streaming. We run hundreds of microservices just to meet all of our metadata needs. One system is responsible for the core metadata, the title and the release year. Another system is responsible for writing synopsis and reviewing the synopsis. Yet another system is there for ratings, and then another system for tagging. Tagging is an interesting process in which we take humans and let them watch Netflix content and tell us about that content, providing key data points. For example, they can tag if a content is a humor, or is a comedy, or is sad, or is action-packed. They don't just give us a single yes or no, that was funny or not, but there's a level that they apply. What we do is we analyze these tags, and that's how we form our title groups that are hand-curated using rules, and that's what generates the rows on the Netflix service. All of this rich metadata helps us connect with our members. The great thing about the microservice architecture is that it allows for new categories of that title-related metadata to be added to our ecosystem as needed. The new metadata is defined in association with the overall hierarchy, and then from there, our internal teams collect the data, and we make it available to our member-facing service. As an example, the base entity that we model is called a video, and it's referenced by an ID. Each video ID uniquely represents a piece of content in our system. It could be a show, or a series, or an episode, a film, or a trailer. Every item gets its own ID. From this base video entity, we then model the relationship with the various pieces of metadata that we need to describe it, which we call a complete video. One of the challenges introduced by operating a service at a global scale is that need for localization. Since not all of our members speak the same language, we must translate that content from the original language into local languages. Without that localization, we would not be able to connect our global audience to our content. But localization adds a layer of complexity and dimensionality to almost all facets of our metadata. Not only does the content need to be localized with subtitles and dubbing, but all of the metadata about that content also needs to be localized as well. In addition to the obvious things like synopsis, we also have to localize the title. The title of a show in one country or in one language could be completely different than the title of the show in another language. Likewise, each country has their own rules around maturity ratings, so those must be localized as well. Another key aspect of translation, aside from just converting text from one language to another, is we're storytellers. We have to maintain that creative intent and that creative meaning. How we use language is a key part of that storytelling process. To do this at scale, we leverage many different tools to manage that localization process. We use translation memory to help ensure that the same phrase is translated the same way throughout the entire piece of content. This tooling leverages machine learning to also help flag and detect when those rules are broken, to see if that same content may be used in a way that it shouldn't be used. All of these tools are used by our expert human translators, which increases their accuracy and efficiency. The tooling also makes sure that the timing of the subtitles is aligned and within expectations that our members expect, because not all languages have the same pacing or use more words or syllables to convey the same meaning. So now that we've filled in some of the metadata, one thing is still missing: the artwork. So our goal is to go from that to this. It's been said that a picture was worth 1,000 words. At Netflix, we agree with that statement. We've ingested more than 10 million images over the course of our history. Nothing grabs a person's attention faster or conveys as much meaning as an image. But because images are so powerful and pervasive on our service, we've had to create specialized tooling to manage that scale. So we first start with defining asset types, which dictate how and where on the service they'll be used. This is a common example that most of our members are familiar with, which is the titles, the images of the titles that appear in our rows. But there's actually two variations, a vertical and a horizontal. Which one we use depends on the use case for that particular screen or that particular device. We also ingest the stylized logo for our content, which typically, and we also do story art, which is kind of key scenes from that content. Much like the encoding process we described, each of those images, after being uploaded, goes through a conversion process to normalize the format and make it compatible with all of our devices. As part of this, we also create multiple different output sizes for each image. It may be easier just to create one and let the devices do all the work for us, but what we found is that by pre-scaling those images, not only do we save on those network bandwidth costs, but the devices are more performant as well. Those two images in the middle, yeah, they're different by about 3 pixels. The design team wanted them to be different so that they could use them effectively on their UIs, but we had to make a whole separate copy of our entire image set just for those 3 pixels. So for those following along, we're already up to 4 different image types, and now we have all these different sizes to create as well. But that challenge of localization with our metadata also applies to the artwork. Whatever title we use for a particular language, we also have to apply to the artwork as well. This means that if we want to localize a title in 30 different languages, you got it, 30 different artworks. Each will have to be overlaid and approved by a human. And without specialized tooling, these would have to be created by hand. And for a long time, this is how we operated. Now, as you can imagine, it's also very inefficient to be this way. Not only inefficient, it's also inflexible. We love to test new things at Netflix. Let's say we wanted to test a new image size on the device for our existing assets. Since every image is pre-created, we'd have to scan through our entire catalog and recreate those new images. It's inconvenient, but at least it could be automated. More disruptive is if we wanted to introduce a new asset type. Our artwork team would have to go through the entire catalog and manually construct those new assets. This process could take weeks, if not months. So to solve some of these problems, we've moved from a statically produced images to dynamically produced images. So rather than having a human manually place logos on top of the artwork, We use composition by having them upload the key components, and we let the systems do the rest. So we create this recipe that describes what combinations of images to use and what output size to create. That recipe is encoded as part of the URL that the Netflix devices use to fetch the images. The image creation service parses that request, fetches the source file, or multiple if it's needed, and it produces the output image according to that specification. It does this all at runtime. Once it's done, it saves a copy of that file up in S3. If the same request is seen by that image service, it doesn't need to recreate it, it just fetches it from S3. But to support our global distribution, we've added features to OpenConnect to act as a cache for those images. So now if a request hits OpenConnect and it's found, we use it. It's nice and close to our customers. If not, we go to our image service. So dynamically creating images has dramatically reduced that amount of work that our teams have to do in order to backfill and test out new image assets. We can also tag key parts of the image, including focal points, so that way we can reuse these images in new and creative ways, all by machines and by these recipes. That single image can be used without having to do large-scale backfills. Developers can also tap into this and use it for their prototypes and their designs. Likewise, we can leave enough space for from those focal points so that we can position our UI elements around them. So again, this happens automatically without any human interaction just because we have those tagged images with the focal points of what we want to use. So to manage all of this metadata, a single piece of content has to go through all these different workflows. We've helped to manage all of that. We've built a system called Conductor, which has also been open sourced, which is a workflow orchestration engine. Conductor allows the engineering teams to dynamically define their own tasks. These reusable tasks accept well-defined inputs, perform some work, and then produce some well-defined outputs. They're connected together to form all these different workflows within our ecosystem. It supports synchronous versus asynchronous APIs, and once a workflow starts, that orchestration engine handles the remaining aspects of the life cycle of that workflow, including scheduling and queuing and timeouts and retries. So having that workflow orchestration engine has enabled us to think more broadly about the tasks that individual services provide. By focusing on the tasks rather than data models or API calls, those tasks are abstracted away and can be used in other workflows. For example, uploading a file is a very common task in our ecosystem. Rather than couple that upload task within an API call, that upload task itself is a key part of those workflows. The workflow engine supports branching and decisions, allowing for very complicated workflow trees. So much of this work that we have to do during title setup is done asynchronously. It's done out of band. Maybe you fire off an email and wait for the response, or you're waiting for a file to upload. This workflow orchestration engine really allows us to do that at scale. There are thousands of different workflow tasks that are executing millions of these each time a day. So delivering all of this rich metadata to our members offers a unique technology challenge in itself. Each microservice is sized for its primary responsibility, which is to process, handle, and store the incoming metadata from our internal operations teams. That workload is typically very write-heavy. It also must be consistent so that if we write a value, we want to read the value back right away. But it really only needs to service a couple thousand people internally. Because of those usage patterns are dramatically different than our external member-facing service, which tends to run in the hundreds of millions of users. So all of that complexity we could try to solve with one giant system or one solution. Rather than that, we've built our own system that we call the Video Metadata Service, or VMS. VMS is built on top of Hollow, which is another open source technology that we built, which is best described as a total high-density near cache. Each cache, or being a cache, it means that the data is a copy of the source of truth. It itself is not source of truth data, it's just a copy. Total means it's a complete copy, not a partial copy. That means there's no eviction and there's no cache misses. Either the data is present in VMS or it's not. Near means that data is in memory, local to each instance. And finally, high density means that data is encoded, it's been bit packed and deduplicated to optimize that memory footprint. So to populate each VMS cache, or to populate the VMS data, each source of truth system that owns metadata publishes a copy of it using a well-defined schema. The Hollow library facilitates publishing the data by leveraging code generation to convert that schema into Java-based objects. The source systems publish data as often as they need it, or as often as they can tolerate a full scan of their database. Remember, it's a full copy of the data. We also support events, however, so that way systems can keep up to date without having to do that full database scan. After each system publishes its data to S3, the VMS service takes over. It runs a transformer service. This transformer service consumes each of those inputs and applies business logic. While the results are being processed, it's compressing the data and removing duplicate records, and the output of that is a superset of all of the fields needed by the Netflix service. It's a full copy, remember. All of the input data is included in those outputs. It's versioned and written into S3. Then the transformer announces that a new version of that data is available, and every instance that consumes VMS goes to S3 to fetch the latest version. Using the Hollow framework in this way gives us enormous benefits, not only from a reliability perspective, but from an operational perspective. Having that data decoupled from the source systems allows for better isolation. This means our source systems could be down for maintenance or for upgrade without impacting the availability of the data to our member service. By having a versioned, complete copy of the data, we can also halt the new flow of data to the service just by stopping that transformer. This allows our internal teams to continue to work just like they would while we investigate and triage whatever might be impacting our data. Likewise, if we need to roll back to a previous known good state of data, we can re-announce that previous version. Since it's a complete copy, the systems can download that full version and we can continue to operate, and they won't move forward until that new version is announced. Data versioning also allows for a concept we call region staggering. We run globally in 3 different AWS regions. Rather than publish the data to all 3 regions at the same time, we only publish to one region first. After waiting for about 30 minutes, then we publish to other regions. What this does is it protects us from bad data causing a global outage. It's happened. Even better, we can publish that data to even only a few instances. So that way that data becomes a test case or a data canary, which is typically pretty hard to do with a normal database architecture. Another great feature of the Hollow framework is that it has built-in diffing capability. In addition to publishing a full snapshot of data for every single version, Hollow also publishes a delta file. The delta contains only the records that were changed, which includes additions, modifications, and deletions from one version to the next. So while the full snapshot of data is produced and is quite large, on the order of hundreds of millions of objects, the delta may contain only 0.01% of that. This reduces the time that those clients need to fetch the latest version of the data. Also, with tooling, we can now inspect those deltas to see how the data is changing on our member-facing service. That those deltas allow us to identify if we need to roll back, which version do we need to roll back to. So as a practical example, all of the metadata that we talked about for every title, in every language, and every country of our catalog can be reduced down to a file that's only a couple gigabytes in size. This data is indexed and loaded into memory of all of our edge services. It supports fast lookup via a code-generated API, and so this data access is strongly typed. VMS has enabled Netflix to scale our member-facing service without having to scale our data layer access. So far, we followed the content on its journey from the metadata systems needed for promotion to some of the encoding and deployment systems we need for playback. But where does that content come from? What is its origin and how is it made? So there are a lot of activities that go into producing content. Contrary to popular belief, you can't just throw data or algorithms at the problem and expect content to come out the other end. It still takes a lot of good judgment, a lot of good decision making, but most of all, creativity. Our aim is to build a platform in which we equip those decision makers and those storytellers with better tools and as much data as we have. This allows them to flex their creativity and tell those stories that we want to be told, whenever and wherever possible. One of the ways we're doing this is with the creation of a central place to coordinate and store all of those various assets. We're calling this the Netflix Content Hub. So prior to Content Hub, the only files that we received were the ones that we needed to support playback. As we started creating our own content that we owned, we had to put it somewhere. So we needed a place to store it. It's not just the final outputs, but all of the intermediate files that go along with it. The shots, the cuts, the visual effects, the audio stems, the sound effects, the project files, the mixes, just to name a few. So for that, we built Content Hub. Getting all of this data, sometimes petabytes per project, at the end of a production can be a challenge. Transferring that much data, even at gigabit speeds, can take days. So to help us offset some of that time, we leverage AWS Snowball whenever possible. Using custom tooling within Content Hub, the production teams can place an order for a Snowball and manage their deliveries right within Content Hub. Files transferred to Snowball appear in Content Hub, providing that visual feedback that they're on their way towards ingestion. Once the Snowball is shipped back to AWS, the status of the files in Content Hub reflect that, and then it can be used to fulfill those archival requests. The archival use case, though, is just the beginning for Content Hub. Our hope is to continue to develop that platform and infrastructure to receive files earlier and earlier in the production process, not just when the production is complete. Earlier access to content not only eliminates that archival process after the fact, but can also lead to better collaboration within the tools. Since filming can happen around the globe, having that footage uploaded to Content Hub, we can enable multiple teams from disparate locations to coordinate and collaborate to tell the stories they want to be told. Further, we can layer in automation needed to provide additional productivity and efficiency gains. Even today, with a button click in Content Hub, you can take a piece of content from Content Hub through our encoding pipeline, through the deployment pipeline, and actually end up with your own personalized row on the Netflix service. This row can be shared with our creative team so that as they're producing content, they can see exactly how the member experience will be once that content is delivered onto Netflix. But in addition to moving files around, there's also quite a bit more work that goes into producing content before the first shot is ever filmed. From the pitch itself, to deal making, casting, budgeting, scheduling, location shooting, script planning, lots more. Each of these tasks can be paired with technology to make them more efficient. Not for the purpose of reducing costs or replacing jobs necessarily, but just to enable those creative content storytellers to do what they love to do most, which is to create new stories. So early on in that creative process, the amount of information that we have is actually somewhat limited. We heavily lean on that creativity and that decision making. And as we get further along in the process, we layer in as much information as we have, which influences more of those decisions. At no point do we turn these decisions over to the machines. One example where we're leveraging our existing systems to help with this production is in the case of tagging. So that same tagging metadata that we use to group titles for rows of titles for our Netflix members, we can use during that pitch process. When a pitch comes in, we can analyze it and apply some key tags, and then the system can help identify what other content is that similar to. It might help predict how it would perform, or does it fill a gap in our catalog? Likewise, we can flip that around and say, look at our catalog and see what kind of content is missing. So not only are we developing tools for use on the production office, but we're also going after those workflows that exist on set during filming, bringing with it a whole new set of challenges and opportunities. One of the most interesting parts that I learned about the production process is the reliance on paper, not just paper, color-coded paper. Not just color-coded paper, lots of color-coded paper. If you're looking at a white piece of paper and you see somebody with a blue piece of paper, you know you're behind. This is how they do versioning. So we're trying to incorporate technology into a space that's operated in this way for a very long time. But it's kind of hard to argue with reliability of paper. When was the last time a piece of paper stopped showing you the data that you just put on it? Even if you lose it or destroy the piece of paper, you can quickly reproduce it just by printing a new page. So we're still innovating in this space, trying to find new opportunities to keep growing and to keep telling more stories. Because the availability and reliability targets of a cloud-based production platform must be carefully considered, since even a short delay while on set could cause losses in excess of hundreds of thousands of dollars per minute. Once you get everybody together, all the props, all the cast, all the crew, all the cameras, all of that, downtime could cause lost moments of truth, not for our members, but for our storytellers. So that's kind of the end of my story for how a title goes from pitch to play. Even as we expand the scope of our technology to encompass more and broader use cases, our mission remains the same: to deliver the very best quality of experience to our members who choose to watch Netflix, but now to the storytellers who are choosing to create content that will be seen only on Netflix. So although this is the end of my story, it is not the end of the story at Netflix. One of those great things about having a goal such as to get better is that you never arrive. That story never ends. So it's not about the destination, but the journey that we're on to get there. There will be triumphs, there will be challenges, but with that dedication and perseverance, I'm hoping we'll find our happily ever after. Thank you very much. I'm going to hang around up here if you have any questions. I'll also be at the Netflix booth later today. Thank you.